get decimal equivalencies. Oops. And in this calculator, if you wanted to figure out the square root of 26, know which one is larger and whatnot, if you type in square root of 26 and hit enter in this one, it just says the square root of 26. Do you know how to get the decimal equivalent out? What button do you have to press? The double arrow. Good. I just didn't know if you guys remember that. So 5.1-ish. Okay. And that's what you would be doing to try to figure out the idea of which one's bigger, which one's smaller. 4 root 5, same deal. If you hit enter to that, it just says 4 root 5 because it does simplify radical form. You got to hit that double arrow. And then the 2 root 2. Double arrow. Excuse me. So I think the question on one of those was put them in order. Was it smallest to the largest or largest to smallest? Oh, yeah. And then it wanted to say, oh, first question was, are you able to make one that's bigger than the others? So what you could do here is you can just use the decimal to kind of get a rough idea. That's 13, 14 is bigger than 2.8. That's 11-ish is bigger than 5. 5.1 and 2.8. Ooh, I got to add those two together. I don't think that's going to work. So if I do the square root 26 plus 2 root 2, I need decimal equivalent on that one. That's smaller than that 4 root 5. That means I can't make that triangle. Everybody see where I'm going with that? Remember, the sum of 2 has to be bigger than the third. So for that one there, it wouldn't have worked. You would have said no. That's what you're doing. You're trying to get some idea here. So the answer is no triangle. The sum of any 2 has to be greater than the third. There's 3 sides. There are 3 different setups you have to check. I have to check root 26 plus 4 root 5, is it bigger than this? 4 root 5 plus 2 root 2, is it bigger than this? Root 26 plus 2 root 2, is it bigger than this? Remember how those are the 3 you would check. Just so happens with the roots, you have to do a little bit of decimal messing around with the 2. That's why we check. Right. On that sheet, was there anything in particular then? From the internet and all that? Because I know it was pretty straightforward. Kind of easy stuff there. You want to pass that one up then as well. And then we'll go into a little bit of what have we been doing, where are we, what we have going on here. So as you go through So what happens here, guys, is that we have all of chapter 5 this week. Sorry, I'm going to the doctor. I swear, I'm talking about it. I can't do this anymore. With missing last Tuesday, the long break, missing the day yesterday, and then finally dead. We're gonna go kind of run through real quick, basically a short review on everything we've done so far in 5. Today we'll do some of those types of things. Tomorrow we'll get into what's called the hinge theorem, and then that'll lead us into the last little bit of just kind of some very simple stuff as we'll do with the review as far as ordered pairs, how those things work out with that, and then we'll be done with chapter 5 come Friday. So you guys know we're on the same page. We'll be done with chapter 5 on Friday. So going back through chapter 5, one of the first things we did was a thing called the mid-segments. Mid-segments did what? Mid-segments connect midpoints. They connect midpoints. Mid-segment did two things. It's equal to half the side not touched, and it was mid-segment was also parallel to the side not touched. And from there, this stuff was pretty simple. It was the idea, were you working with the actual mid-segment, or did you have the whole segment across from it? Did you have to cut something in half, or did you have to double it? Now, remember, instead of saying the mid-segment was half the side it doesn't touch, we also wrote it as if you double the mid-segment, it equals the side not touched. Okay? That's how those things work with each other. So if you look at something like that. Yep. That real simple example has mid-segments. It says that x plus 5, it touches the two sides of the triangle at the midpoints. You can see it because it's marked. That means it's equal to half the side it doesn't touch. Or, if you double it, it'll equal the side it doesn't touch. What side doesn't it touch? 3x minus 1. So remember, the easiest way to do this was always to do, let's move this up a bit here. If I double my mid-segment, it equals the side not touched. And then from there, it was a matter of just writing it out, distributing correctly, go to both parts. Don't make a dumb mistake. And that's just a quick algebra problem. Variables in both sides equation, what do you do? Just pick on the little guy, subtract the 2x. I'm going to add 1 at the same time. Now remember, sometimes it asks you to solve for x, sometimes it might ask you to solve for the actual segment. If you had to solve for some segments here, what would you do with that value of x? Substitute back in. For example, if we had to figure out what the mid-segment was, what's 11 plus 5? 16. 3 times 11 is how much? Subtract 1, you get 32. And lo and behold, half of 32 is 60. Again, this is really nice and it's easy math. You don't go back and forth and worry about messing stuff up. Or at least hope. Now, after that, we started talking about angle bisectors. And perpendicular bisectors. So if we go back and think about flesh unit. One of the things we did with the angle bisectors, actually we did a couple different versions of this. We said that if you were on the angle bisector, you were equidistant and perpendicular to the sides. We wound up with a bunch of angle side because that point on the, excuse me, the point on the angle bisector was always reflexive. So we were able to do stuff like which meant we did a lot of right triangles, which means you had to use Pythagorean theorem. Where the C value is always which segment? The long. What's it across from? Let me start with that. Which is in a right triangle, which is always going to be the right angle. Okay. Or we can't anything larger than a right angle after that. So, excuse me. So we're looking at angle bisectorism itself here. Here we are. We did stuff. here and there. But these are perpendicular bisectors in circles. Remember, if they're saying that's where all the perpendicular bisectors meet, it was always point to vertex was always the same. Okay? Point to vertex was always the same. Which one of those segments in that picture is given to you as a point to vertex? I'm sorry, I'm ahead of you guys. You guys are still drawing this out. Sorry. There's three of them, but which one's given to you, like numerically? Right. So again, if you know that's where the perpendicular bisectors all meet, is at G, then you know that these are all right angles on the outside of the triangle. These segments have all been bisected. And you can start filling in blanks. If from the point to vertex is 25 for one of them, what does the point to the vertex for the other two have to be? It's be the same thing. This is 20. This is. And then again, it goes back to the idea of how do you solve for the missing side length if you have right triangles. Okay. That was about as complicated as most of the stuff got, is that you just had to use Pythagorean theorem a couple of times. It's lovely how they just keep saying, use Pythagorean theorem. You don't learn about it until February. So, which value there is, it has to be playing the role of the C? 25. 25 is always going to be the largest side because it's got to be across the largest angle. We learned that later on. Yes, ma'am. You could have, if you think about it, when you have Pythagorean theorem, how many variables are there? How many do you need to know? So you could have A and B, find the hypotenuse. You can have a leg and one of the legs and the hypotenuse. It doesn't matter. As long as you have 2 out of the 3, you're fine. Okay. As long as you have 2 out of 3, you'll be fine. So then here, something squared plus 20 squared is 25 squared. In your calculator, you can do a lot of this as one giant step. You don't have to square it and rewrite it down. You know you have to move that 20 squared to the other side. In your calculator, you can just type in 25 squared, subtract 20 squared, and hit enter. I talked about this when we did this a week or so ago, about how to take the square root of an answer. Remember that? You take the square root of the answer. Hopefully you guys get used to using the answer button because that's going to come in super handy when you guys start doing sine, cosine, tangent, trig stuff. Second, square root, second, answer. And it's going to automatically dump in there that 225. That way you don't have to rewrite it. It's not so bad now because they're just regular numbers, but when we get into trig, you're going to have a lot of crappy decimals. You don't want to be writing down a whole bunch of crappy decimals. You don't want to just let the calculator do the work for you. Let it take care of it for you. Plus, then you won't have as much rounding error. More precise you are, the better. Okay. All right. So that's how you get those missing side lengths. That one's wind up being 15. You do the same thing for the other one. Here you've got a 15 and a 25. Well, if you know that's 15 and a 25, what does that other side have to be? 20, because you just solved that a minute ago. So that one's going to be a 20. The last one, though, is this little guy here. 24 squared plus something squared. Again, just type it in the calculator, moving it over. And what's the square root of 49? Also, one of the things we'll talk about when we get into second semester stuff, with right triangles, there's these things called triples. Triples are numbers that, number patterns that will always work for right triangles, whatever scale factor you put onto them. For example, what's 3 squared? What's 4 squared? What's 9 plus 16? What's the square root of 25? 5. So one of the triples that we start learning about later on is something called a 3, 4, 5. If I double each one of those, what do you get? What's 6 squared? What's 8 squared? What's 36 and 64? What's the square root of 100? 10. This is the 3, 4, 5 is the most common, or probably the most widely used geometry thing you'll ever see. Have any of you guys, I don't know if I brought this up before, have any of you guys ever helped build, like, frame a wall or put a patio in or anything like that? Yeah. So when you're building or frame up a wall, you don't want your walls to be wobbly. You don't want your walls to be not square. Your hanging cabinets, you want to make sure, you guys know what a shim is? A little wood shim, you put something to help move things back and forth from the walls and whatnot. What happens is you will measure out 3 feet in one direction, 4 feet in another direction. From those 2 points, it should be 5 feet, because if it is, then you're square. If you go out 6 feet, 8 feet, it should be 10 feet. You can use these patterns to help measure to see if you're maintaining squareness as you're building walls and stuff. So. Yes, ma'am. Yep. Multiply it by 7. Then use your calculator. You get what? 21, 28, 35. 21 squared plus 28 squared. Square root of that. It even works with fractions. If I divide them all by, if I multiply them by a half, 3 halves, 4 halves, 5 halves, it'll still work. Okay? It's very, very, very common. Now, after we did those two guys, we got to the weird one. The weird one was the centroid. Now, the centroid, when you guys got to the centroids, that's when we had all that 2/3, 1/3. Remember all that? Yeah. Now, the centroids where the medians intersect. The median is the segment that connects midpoints from the vertex. Right. And we called it vertex to centroid. And then we had centroid to side. Remember all that? Do you remember what the relationship was? See if you remember that. See, if this was 8, what was that side? So we had 4 different ways of writing this thing out. When we did that, vertex, centroid, side. Remember how I said, hey, let's take it out of the triangle and put it as just a line. And we wrote it out in terms of words. I'm going to shrink this picture here for a second. We said 2/3 the whole thing equals vertex to centroid. 1/3 the whole thing equals centroid to side. But those weren't the ones we used all the time. The ones we used all the time was the relationship between the two parts. We knew that, like you guys just said a second ago, the vertex to centroid was 8, centroid to side was just half. Because half of 2/3 is 1/3. If I double 1/3, I get 2/3. So the relationship between the two was the one that we usually work with. So if we double centroid to side, it equals vertex to centroid. And the last one was take half of vertex to centroid, and it equals centroid to side. Those were the 4 common things that we had. And hopefully that doesn't sound so horrible, bad, so long ago. The worst case scenario again here, we had some algebra thrown in there. It wasn't that the algebra was tough. You guys just forgot to take half of the second piece or forget to distribute out completely. You're an asshole. So, as I said, this wasn't, it just looked like it was awful, but remember, it was more along the lines of, okay, if this much here is 5, is that the whole thing? Is it vertex to centroid or is it centroid to side? Okay, what do I do to it to figure out the vertex to centroid? Double it. All right, what's double 5? 10, which makes the whole thing. Same idea. If I say this whole thing, if I say the whole thing is, I don't know, 27. I'll do 30, make it easy. What was easier to find? The smaller section or the larger section? Smaller, remember? Because get the smaller, what's 1/3 of 30? What's 30 divided by 3? 10. So that's what we did. The whole thing was 30. That means this much is 10. And then this much would be 20. Okay. Yes, ma'am. Oh, I thought you went like that. Yes, sir. Because this part here, this is vertex to centroid, is 8. Centroid to side would be half of it would be 4. Not drawn to scale. Just think of it that way, not drawn to scale. I'm just throwing numbers out there that I know that would work clean. Then the last little bit, what you did last week was your angle order. What did this double arrow represent again? Remember? No. I see what you're saying across from, but remember when I wrote it, instead of writing it out 2 times, it means the same thing going both directions. The longest side is across from the largest angle, the largest angle is across from the longest side. It's sort of this one double arrow. then the last little bit was when we did the find the range of values. We found the range of values for missing side lengths. That was that real quick algebra. So if you had side lengths of 4, 7, and something, you wanted to find the possible range of values. Remember the shortcut? What was it? Correct. Yep. Remember the idea was that always the sum of any two is always larger than the third. When we did this, we always wound up with one segment that wound up with being a negative value. So over time, we realized that the shortcut was add them together, subtract them. So what's 7 minus 4? What's 4 plus 7? X has to be bigger than 3, but smaller than 11. That was the trick. That was the trick. Those symbols will always be like that. They'll always be less than symbols and go from there. It should be so. So, made for you guys real quick. Sorry. On this, there's one of them on here that I forgot to cross off or made a copy. So, if you guys flip around, it looks like there's only one number 18. Yeah. Cross off the one that says number 18. Draw an obtuse triangle ABC. Cross that off. Cross off where it says draw the obtuse triangle ABC. I forgot to block that out before I made the copy. Okay? So that's the only one. The rest of it should be really quick. There's a lot of review. We'll get into that thing called the hinge theorem tomorrow. Pretty much. About how a lot of stuff works.
Mystery second.
Hey, what? How's that?
I got Al, Chris, and Al. So they're all there too. Emma wasn't. Didn't forget to tell her. But she's like, yeah, I'm good. I'm like, all right, go put it in now. I forgot. We need to figure out.
I can't.